All right, we're going to take a look at chapter 13 today, starting with sound waves. Sound in air moves like a type of wave like we talked about before. If you clap your hands, it produces a sound pulse that goes in all directions. Okay? If you stand in the middle of the room, clap your hands, everyone in the room is going to hear that clap. Every particle moves back and forth, okay, along the direction of motion of the expanding wave. So as that particles move back and forth, that's what's producing that sound wave. The compression travels along the air spring similar to the way the sound travels in the air. So when you clap, as you go this way along, there's a bunch of compressions and refractions in here. And that compression and refraction is what allows the sound to travel. That's what allows that sound to go. Now this shows it one-dimensional, okay, or moving in one dimension. This is happening spherically. It's happening in all dimensions. So looking at this slide, we can get an example of a door opening. Now, air doesn't compress, but the energy of the waves will. So when the door opens down here, it pushes out and it moves this the window covering over, pushes it out the window. That is a compression. The refraction, now when the door shuts, in this case creating a vacuum, okay, or that expansion, the curtain pulls into the room. So quickly opening and closing that door is pushing the molecules in that same manner, or pulling those molecules in that same manner. The neighboring molecules then push into their neighbors and so on, and that's what causes that compression. It kind of moves down the line. The pulse of the compressed air is the compression now. So now it's that compressed air is moving along. Closing the door kind of works in the opposite way. It produces an area of low pressure, okay? So those nearby molecules move in, leaving a zone of lower pressure behind them. The molecules next to those move in, and that creates a chain effect of low pressure, and that's called a rarefaction. For all wave motion, it's not the medium that travels across the room, it's the pulse. Just like in the water, the water's not moving. The energy is moving through the medium. The water just moves up and down. Same thing with the air, okay? The pulse travels from the door to the curtain. The air is just the medium that moves it in. It'll move back and forth a little bit, but it's that small medium, or it's the medium that lets that energy go through. This happens on another scale with a speaker. If you've ever looked at a speaker, taking the cover off, you notice the speaker moves back and forth. Well, that works the same way as opening and closing the doors. It's a smaller scale, and it happens much quicker. And that's going to produce pulse of air. And those pulses of air is what's causing or making the sound that's coming out of it. Vibrations from a tuning fork back and forth, those can make sounds, typically a higher frequency. So here's the tuning fork. So when the prong of the tuning fork next to the tube moves towards the tube, the compression enters the tube. It goes this way, and that's what we see here. And it's going to knock into these particles, and those particles move along, and this wave, or these pulses of wave, move along. Okay, so we have these compressions and these rarefactions moving through this tube, and that's going to produce a sound going. When we talked about frequency, there's a subjective measurement to it, and we call that pitch. Okay, as we hear the frequency, we say there's a certain pitch to it. A high-pitched sound from like a piccolo has a high vibration frequency. Low-pitched, like a foghorn, has a low vibration frequency. Now, waves can be used for many different things. Frequencies below 20 hertz are called infrasonic. When they get above 20,000 hertz, they're ultrasonic. And these waves can be helpful because these can help produce images for us. And what they do is when the waves move, they bounce back at different rates from different densities. And by doing that, by getting these waves back in different times, in these different off these different densities, it'll make a picture for us. So we can use the ultrasound machine to be able to get pictures. Dogs can hear frequencies of 40,000 hertz. Bats can hear up to 100,000 hertz. So they get to much higher frequencies than people. We can't hear infrasonic or ultrasonic. Now the speed of sound depends on the medium. Now, we talked before that wave speed depends on the medium, not the wave. Okay. Typically sound travels through solids, liquids, and gases, and the speed depends on the particles that it's passing through. Typically solids, the sound will travel quicker through because those particles are typically closer together, and one will bounce off the other much quicker, and it'll go through the solid much quicker than it goes through the gas. So sound waves travel faster through solids than they do gases. Sound, we talked about, travels in 3 dimensions. It makes what's called a spherical wave. If you stand in the middle of the room and clap, everyone in the room, top, bottom, left, right, front, and back, wherever you are in that room, you're going to be able to hear it. Now, the Doppler effect, you guys have probably all heard of Doppler radar, and it kind of uses the same technology or the same effect to do it. But I'm sure that you have all heard like a siren coming down the road, and as it gets closer and closer to you, it's getting a higher and higher pitch, and then it passes you, and as it goes away, it gets a lower. And the reason that happens is as the car travels towards you, look at what happens to these waves. Okay, it lets this one off, but then as the car moves, that sound wave's closer and closer and closer. So as it gets closer to you, there's a higher frequency. And then for the opposite reason, when the car moves away, these sound waves are pulled farther away, so it has a lower frequency. And this is called the Doppler effect. And this same thing is used in weather by being able to find density of clouds and how quickly they move, and that'll be able to tell you if rain is coming or not. So because frequency determines pitch, the Doppler effect affects the pitch heard by each listener on the street. The observer in front of the car hears a higher pitch, while the observer behind the car hears a lower pitch. And it all has to do because of the movement, because of what's moving closer. It's causing a greater frequency as the car moves closer and a lower frequency as the car moves away. All right, so you should have gotten your assignment for 13-1. And on 13-1, your assignment that you should have gotten was page 486, the section review now, and those were questions 1 through 5. So that pertains to what we just talked about here. So now you should have those done and completed. Turn those in if you do. Now what you should do is get this done, get it turned in. And tomorrow you're going to read 13-2, and you're going to get that, an assignment on that, and get that turned in. But for today, make sure you get this assignment done and get that turned in.